present Jan-Philippe Solovej, which is currently the president of the European Mathematical Society. To give you a little bit of short view, he was a collaborator of, or is, I don't know, of Elliott Lib, especially at the beginning when he started his PhD in Princeton in '89, and was also assistant professor for several years at Princeton. And then he come back to his homeland, which is Denmark, and he went to Aarhus in '95, and then is now since '97 in Copenhagen. His research, he's doing mathematical physics also for quantum mechanics. I mean, structures and stability of matter, basically, related to, small things like atoms to larger things like stars. He got, I think, the most prestigious prize in mathematical physics, which is the Henri Poincaré Prize in 2021, I think. And so that's the main prize given by the International Association of Mathematical Physics. And so he's also leading a research group in quantum mathematics for quantum theory. I mean, an institute, a department, research center. And so he's going to speak about dilute quantum gas, namely Bose and bosonic gases or fermionic system, which was very would get very fashion in the end of the 80s because of this famous experiment producing Bose-Einstein condensation in 1995. And then there were a lot of activity, both on experimental level, but also in mathematics, starting with Lee-Huang-Yang in '98. And so, please, so we are happy to have you. No, you don't need this.
Thanks a lot. So it's a great pleasure to be here. And indeed, I will talk about quantum gases today. So right now, my research is really focusing on two things to do with quantum gases or atoms. So these are the two things that I have basically done most of my life, and I go back and forth. So my love is sometimes more with quantum gases and less with atoms. Right now, I'm actually a little bit more with atoms, but I will tell you some of the work we have done on quantum gases. And this is joint work with 3 former PhD students, Agerskov, Fournais, and Reuvers. Reuvers was for 5 years ago graduated, or maybe 6, 7. Agerskov just graduated, and Fournais, that's more than 20 years ago. So it's hard to think of him as a student anymore, but he was at some point. So here's the talk. I will both give you an overview of quantum gases and then some of the results that I have been involved with. So I will simply start telling you about many-body quantum mechanics. And I should say right away that what I'm interested in here is the thermodynamic limit. So large, infinite systems, if you want, so systems that we think being of laboratory size. There's a lot of work being done also on confined systems, but I will actually not review that. There's even more work on confined systems because it's slightly easier to work with confined systems. But I will only talk about the thermodynamic limit. I'll give you some examples, and I'll explain what happens in 1, 2, and 3 dimensions. So in order to explain it, I have to introduce the scattering length, which comes from just 2 particles interacting. So since it's a dilute limit, there are very few particles per volume or area or length, depending on which dimension you're in. And when there are very few particles, you may think that the largest contribution is coming from just 2 particles interacting, and that's actually what we will see is the case, and 2 particles is described by the scattering length, which describes the interaction of the 2 particles to the order that I'm interested in. I will give you some exactly solvable examples. They are in 1D. And I'll talk about what we expect for the bosonic ground state for Bose particles. I'll explain Bose particles, Fermi particles, so on, in 3D. And then I'll review the rigorous results that we have for bosons in 1, 2, 3 dimensions, the rigorous results for fermions. There are not that many for fermions, actually. Fermions are more, strangely enough, more complicated. I'll talk about experiments. So Jean-Bernard mentioned already that there were, of course, the experimental verification of Bose-Einstein condensation. But there's also been more detailed experiments on the things that I'm interested in. I should say right away that Bose-Einstein condensation is an important phenomenon for bosons. We cannot prove it mathematically for a thermodynamic system. So it's actually one of the holy grails to prove Bose-Einstein condensation. And much of what we do is to do things that we can do without having proved Bose-Einstein condensation. We're still struggling to prove Bose-Einstein condensation. I will then describe the proof of what I know about the ground state energy in 3D from what's called the Bogoliubov approximation. So a little bit of the theory of superfluidity. And I'll give you a very brief overview of the Bogoliubov theory and how it gives us a result in 3D that had been an open problem for 60 years when I solved it together with Fournais in 2020. So I'll finish with a conclusion and open problems. So many body Hamiltonians. So this is the most basic physical system you can imagine. You have n particles in a box. But as I said, I will not be looking at a confined system. So I will not look at my particles confined to a fixed box. I'm going to let the size of the box go to infinity and look at what happens per volume, area, dimension, depending, volume, area, length, depending on the dimension. And the Hamiltonian, so I'm replacing all physical constants by 1, which in a sense is a choice of units. So the kinetic energy is described by a Laplacian, and there is a potential which is a two-body potential that depends only on the distance. And it's a pair potential, so particle I interacts with particle j, where you're summing over all pairs. So that's sort of the most basic physical system you may have, and lots of gases of cold atoms are very well described by this system. Right? Physically, there should have been an h bar squared over 2 times the mass of the particle in front, but I'm setting all that equal to 1, which you can think of as a choice of units. Now, the potential that I'll be looking at is very general. In this talk, I will assume that it has compact support. That's not needed. I mean, that you can, if it decays fast enough, everything is still okay, but let's not make it more complicated. It's allowed to be infinity, meaning that there can be hard cores in this potential. I want it to be spherically symmetric, but beyond that, it doesn't have to be continuous or smooth, or it can be just a measure for that matter. And what I will call the free gas is the case when V is 0, right? When there is only the kinetic energy. So I will often compare to the free gas. The other opposite example is the hard sphere gas, which has infinite energy when the particles get to distance r, and it's 0 energy when they're distance bigger than r. So think of them as hard balls, that they don't see each other unless they touch, and then they just have infinite energy. Good, so that's the type of system I'll be looking at. Well, we have to make it quantum mechanics, so we have to put it on the Hilbert space. And the Hilbert space, I'm sorry, let me go back. So the Hilbert space, well, it depends on whether you're doing bosons or fermions. I will always think of my bosons as being spinless. So the bosonic space is simply the symmetric tensor product of the L2 space over this set omega. Or if you want, you don't even have to think about symmetry. You can, so here I said the symmetric tensor product, that's this one, but you can also just think of the L2 space in all the variables, because I will be looking at the ground state, so the lowest energy state. I'll get to it in a moment. And for the lowest energy state, it actually doesn't matter whether you look at the symmetric subspace or the full subspace. Interestingly enough, that was a comment made way, way back by Yang. Yang mentioned, C.N. Yang, who is still alive, I think, 100 years old. He mentioned this to Dyson, who had studied these problems, that if you want to study bosons and if you want to look at the ground state energy, then you may as well forget about symmetry at all, because the ground state will be symmetric. It will live in the symmetric tensor product. For fermions, it's different. You want to look at the anti-symmetric tensor product, so that if you interchange the two positions and if you interchange two particle labels, you get a minus sign. So this is the fermionic property, and the fermions will be allowed to have spin. I said spin J. Of course, physically, fermions have half integer spin, so 1 half, 3 halves, and so on, whereas bosons can also have spin 0, 1 integer spin. But here, I'm introducing the spin only for fermions, because at least they cannot be spinless. And the focus will be on the ground state energy, which is the lowest part of the spectrum of the Hamiltonian that we had on the previous page, this thing here, on the respective Hilbert space, right? So for fermions, when I don't put a label up here, it means it's either bosons or fermions. So, but I will put, sorry, so here I said bosons, I should have put a B here, and I put an F up there, it's fermions. So it's actually what you get by looking at the infimum of the spectrum of the Hamiltonian on the Hilbert space that we have defined. I'm not going to go into details of domains and so on. That's not such a big issue. You can start from very smooth wave functions with compact support, and then you can just do what's called the Friedrichs extension, or you can just minimize over such functions. So I'm interested in this lowest possible energy. And the lowest possible energy, I want to calculate it per volume or per area or per length, depending on the dimension. And then there is a very general theorem that says that you can take the limit as L goes to infinity. The thermodynamic limit, you look at an infinitely big system. I have divided by the volume, area, length here. And you want to keep the density fixed, right? So the density is either particle per volume, particle per area, particle per length. So you keep that fixed or let it converge. You get a function. I'm calling that function E of rho. So there is such a function. It requires a little mathematical proof to show this, but there is such a function. I want to know what is that function. So that function describes the energy as a function of density. If you want, it's an equation of state for your system. So here are a couple of examples. We can look at the free gas. So that was if V is equal to 0. And I'm looking at the ground state. So from a physical point of view, that means I'm looking at 0 temperature. We could also look at positive temperature, but that is much more complicated. So if I'm looking at 0 temperature, then the free Bose gas has 0 energy, because you can put it in a state where you put, since it, for bosons, it's symmetric, so you can take a product over the same function for all the particles. That's a symmetric state. And in fact, you can choose that function to be nearly constant. In fact, if you have periodic boundary conditions, as I said I did, you can choose it to be constant. And then if I go back, the kinetic energy here, the Laplacian on the constant function is 0, and then the whole thing has 0 energy. So for bosons, you can actually get 0 energy if I have free bosons. You cannot do that for fermions, even when they're free, because you have to put them, because they have this minus sign, so you cannot put it in a state like that. If I interchange two particle labels, I would not get a minus sign. So to be able to do that, you have to put them in different states. That's the Pauli exclusion principle. And that means that you actually get a much higher energy for a fixed density. And there is an explicit function. It's the density to the power d plus 2 over d in all dimensions, actually, 1, 2, 3, and up. And there is a specific constant here that depends on dimension. So that is a famous formula taught in elementary physics courses, the free Fermi gas. I just wanted to point out what it is in dimension 1. It goes like rho cubed. I mean, if you put in d equals to 1, you get 3 in the numerator and 1 in the denominator, and you get rho cubed. With a specific constant that turns out to be pi squared over 3, because it will appear a few times. Now, what I could try to do is to use the free gas, this state here, as a trial state for bosons when they interact. I could say, okay, this, by the way, this is what we mean when we talk about a condensate. This would be a pure condensate. All the particles are in the same state. That will not be the ground state if I have interactions, as we will see in a moment. But I can still use this as a trial state, meaning I can calculate the energy. If I go back here, see, you calculate the energy by calculating expectation values of the Hamiltonian. I can do that in such a state and see what energy I'll get. It's a simple calculation, and you will find if you use that state as a trial state, you get the energy 1/2 rho squared integral V. Right? I mean, you have constant function. Think the constant function as my phi, and you integrate that against a volume, against the potential, sorry, that is V of x. Then it doesn't see any difference, so it becomes just the integral of V. And you do it for all the pairs. And how many pairs are there? Well, n squared over 2 pairs, essentially. So when you calculate per volume, then you don't really get n squared over 2 pairs because not all the particles interact. Each particle see only the other particles within the region of the potential. And then when you divide by the volume, you essentially get rho squared, 1/2 rho squared integral V. So the true bosonic energy must be less than that, because this was a trial state. The true ground state must be doing better than that. So we should keep that in mind, that we should be able to do better than something that behaves like rho squared for interacting bosons. They should be able to do better than the pure condensate. Another thing we should notice is that I can also, that was what I said before, I can use a bosonic state as a trial state also for fermions, because bosons, in having this symmetry that you have for bosons, you don't need to require it because it's automatically the lowest energy. That was this Yang comment. So the energy for fermions, I can use fermions as a trial state for bosons. So the bosonic energy must also be less than the free Fermi energy. And now notice that something happens in dimension 1. In dimension 1, we got rho cubed right here. If you look at the different powers, if you go to dimension 2, then you actually get rho squared. Right? So for the free Bose gas as a trial state, the rho squared, I would also get it from the free Fermi gas. But in dimension 1, the free Fermi gas gives me rho cubed, which at low density is much smaller than the rho squared. So using the free Fermi gas as a trial state in one dimension is better than using the condensate function in one dimension. And it's actually well known that you don't have condensates in one dimension. And I'm actually basically showing that in one dimension I can do better by a free Fermi gas than by a free Bose gas when I try to look at the true Bose energy. So we don't know, is rho cubed the right thing in one dimension, or is rho squared the right thing in one dimension when the density is small? When the density is high, the rho squared is essentially the right thing, but not at low density. But we'll get to that. So keep in mind that if the density is small in one dimension, the free Bose gas does better than the free Fermi gas does better than the free Bose gas as a trial state for interacting bosons. Of course, I should say that I have ignored, when I calculated this, I actually used this energy. So of course there would also be, you might say, oh, wait a minute, you ignored the potential when you use the free Fermi gas as a trial state for bosons. And that's true, except fermions don't see each other when they get close, so they hardly see the potential at all. So that's why this may actually be a good approximation to the, as in trial state for a free Bose, for an interacting Bose gas. But I'll get to that in a moment. Let me get to how we would try to understand the problem. And since it's a dilute gas, you have to look at the scattering length, what's happening for two particles. Two particles is described by just one parameter called the scattering length. And how do we get it? Well, we look at the energy in a volume L for two particles. For two particles, of course, you don't have a thermodynamic limit as such, because the thermodynamic limit required that you had a fixed density. And if you have only two particles, as the volume becomes infinite, the density goes to zero. I can still ask, how does the energy for two particles behave in a large system? And it turns out that you have different formulas in 1, 2, and 3 dimensions. And in all dimensions, they're described by one parameter. The parameter is called the scattering length. It has the dimension of a length in these 3 dimensions. So let's start with dimension 3. Then to leading order, it's 8 pi, some number a, that depends on the potential, times L to the minus 6. And let's just count dimensions to see that it's correct. So A has dimension of a length. I divide by L to the 6th. So that gives me length to the minus 5. Energy in my units, if you go back, recall that I had chosen units so that the energy was like the Laplacian. The Laplacian is 2 derivatives, so that's 1 over length squared. So energy is 1 over length squared. And then I want to do it per volume. So it's 1 over length squared divided by length cubed, which is 1 over length to the 5th. And that's exactly what you're getting here if A has dimension of a length. And it turns out that to leading order for large L, there is a number A so that the energy is 8 pi A L to the minus 6. That number is called the scattering length. In one dimension, well, you can do the same calculation again. To leading order, it will come L to the minus 3, which is again the energy unit, L to the length to the minus 2, divided by length, which is length to the minus 2. And here the scattering length comes in as a parameter standing right there. So to leading order, it's 2 pi squared L to the minus 3. Dimension 2 is more complicated. There's an annoying logarithm, and logarithms are really annoying. But you can see the dimensions are right. Again, it's length to the minus 2 divided by area, length to the minus 4. And now there's a correction, which is again given by a length over L with a logarithm, and that's called the scattering length. So in all 3 dimensions, I have this parameter called the scattering length. For the hard sphere, remember the hard sphere was the thing that the particles saw each other when they came a distance r from each other, and then this energy was infinite. And otherwise, they didn't see each other. And it turns out that indeed that is the scattering length. So for hard sphere, the scattering length is the radius of the hard sphere. So that's also why it's nice to have this parameter, because you can then compare any other potentials to the hard sphere. Right? If a potential has a scattering length A, it looks a bit like a hard sphere with that radius. For the free gas, well, you would think the free gas has A equal to 0, scattering length is 0. And if you look through, that's actually correct in 2 and 3 dimensions. But in 1 dimension, actually, the free gas is, and this is related to this rho cubed, rho squared thing we had before, the free gas is very far from being being dilute, if you want. So it has actually infinitely long scattering length. So it's and the scattering length, whether it's plus infinity or minus infinity, actually you should think of the scattering length living on the circle. So plus infinity and minus infinity is really the same. But for d equal 1, one has to note that the free gas has infinity, right? Because this term here should actually disappear in that case. Right? And you should end up just with the L to the minus 1. Now, the dilute limit in all dimensions will be that interparticle distance is long compared with the scattering length A. So that basically means that the number of particles that you see in a ball of radius A is very small. So the dilute limit is rho A to the D going to 0. And that's the limit I'm interested in. So let me just point out that in 3 dimensions, how do you get this 8 pi A L to the minus 6? You should think of it that actually the two-body wave function is essentially a thing that's translation invariant. It's a function U, and you have an L minus 3 for normalizations. And this function U is what's called the zero energy solution, the zero energy scattering solution. If you pick that function, plug it in as a trial function, you will reproduce that number. So that's important to know, that to think of it in this way, at long distances we wanted to go to 1. So this is essentially the function 1. So when I square it, I get L to the minus 6 essentially, and I integrate over 2 variables in a box of size L, so it gives me 1. So this is the right normalization to have. It's sometimes, this function U turns out to be between 0 and 1, and it's sometimes useful to think of it as 1 minus a function omega. So it's the scattering solution can be useful to think of it as how far is it away from it's essentially 1 everywhere, and then it dips down when the 2 particles get close to each other. And that's described by this function omega. And there's an explicit formula for the scattering length. It's 1 over 8 pi integral V times U, or V times 1 minus omega. And since U is between 0 and 1, this is much less than 1 over 8 pi integral V. In fact, if I had the hard sphere case, then V is infinity when I'm inside distance R. So for the hard sphere case, this would be infinity, which is certainly bigger than A, because A was the radius of the hard sphere. So this is of the extreme case that the integral of V can be much, much, much bigger than the scattering length. And that is related, somewhat related to this fact here, that the Bose energy is less than that. We'll get to comparing a better estimate than the 1/2 rho squared integral V in a moment. Let me give you some exactly solvable models, and this is in 1 dimension, as I said. It turns out that the hard sphere gas in 1 dimension doesn't matter whether you do bosons or fermions. They're the same, because if it's the hard sphere gas, the particles cannot move through each other. So they don't care about a sign. Right? You just solve it when they're ordered, and then when you want to make them bosons, you reorder them without putting a sign, and if you want to make them fermions, you order them with a sign. They have exactly the same energy. For the hard sphere, it doesn't matter whether you do bosons or fermions, they have the same energy, and it's actually an explicit formula right there, because you can actually think of it as a Fermi gas, where you have just removed the volume coming from the hard sphere. So it's basically a Fermi gas in a smaller volume. So you get a higher energy. There's a 1 minus rho A to the minus 2. Remember, the pi squared over 3 rho cubed was the Fermi energy, the free Fermi energy, and the interacting gas has higher energy than that, given in terms of the scattering length. Another example that you can do explicitly is what's called the Lieb-Liniger model. That's a delta function gas, where the potential V is a delta. As I said, that there could be a measure. C here, you should think of it as being positive. So the particles do not see each other until they are on top of each other, and then it's a delta function. You can solve it explicitly. It was done by Lieb and Liniger in 1963. And let me not give you the formula. It's complicated. There's some integral equations you have to solve. But I can give you the leading order term. And notice I've written it in exactly the same way as I did for the free gas, because it has exactly the same expression to leading order. There's a rho cubed, and then there's the correction. This is the solution that you get from the Lieb-Liniger model if you use A to be minus 2 over C, and that's exactly the scattering length for the Lieb-Liniger model. It's negative. The Lieb-Liniger model, the delta function, has negative scattering length. But, so I noticed this at some point, I don't know if it had been noticed before, that the two formulas are exactly the same if you write them in terms of the scattering length. So I asked myself, maybe this is always true. And indeed it is. This is the right formula for all potentials to next to leading order if you consider abstract potential, general potentials, and you put in the scattering length for that potential. But let's get to that in a moment. I emphasize here a universality, that it's universal for all V, it depends only on one parameter. Let me get to the three-dimensional case. Here we cannot do an exact calculation, so we have to do approximations and prove that these approximations are correct. So, but here's a very nice calculation you can do in 3 dimensions. This calculation, by the way, is wrong in 1 and 2 dimensions, but it's correct in 3. Well, I will prove that it's correct in 3. I'm looking at a dilute gas. I know the energy for a pair. Well, I mean, the energy, if the gas is dilute, must be the number of pairs times the energy of a pair. It seems reasonable. So I take the number of pairs, n times n minus 1 over 2, and then the energy for 2 particles. And then you calculate, this is n times n minus 1. You use the formula that we had for the scattering length. That was this formula here, 8 pi a L to the minus 6. You plug that in, 8 pi a L to the minus 6, and the n minus 1 over 2. And you take the limit L going to infinity, n over L cubed going to rho to get the thermodynamic limit, and you end up with 4 pi rho squared A. So that seems to be the right leading order. And indeed it is. So the calculation I did here actually goes back, I think, to Lenz 1927, this heuristic calculation. Dyson started getting interested in this problem in 1957. I usually call 1957 a golden year in condensed matter physics because there were so many important papers published that year. This is one of them. Dyson tried to prove this formula. He realized we should be able to prove it. I think this is the first paper, I want to emphasize this, the first paper in many body quantum mechanics that is mathematically rigorous. So mathematical physics of many body quantum mechanics was born by this Dyson paper in 1957. Dyson proves that this is correct to leading order as an upper bound. He couldn't get it as a lower bound. He got it wrong by some factor, 1 over 16 smaller or something like that. And it took another 40 years before Lieb and Ingwersen, Jean-Bernard pointed it out. In 1998, they proved that this is indeed correct. Before I go on, let's compare this thing to the approximation we had a moment ago. Right? This is what I got if I use the pure condensate as a trial state. 1/2 rho squared integral V. We know now that this, for small rho, is rather 8 pi a rho squared. Right? So the rho squared indeed is there. The rho squared is the right power, but the constant is 8 pi a and not 1/2 integral V. Notice that 1/2 integral, I have to go here, 1/2 integral V is much bigger than 8 pi, is much bigger than 4 pi a. Right? If I pull 4 pi over here, I get that 4 pi a is less than 1/2 integral V. And in fact, they are way off if you look at the hard sphere. The hard sphere would have been, this estimate here for the hard sphere would be infinity, and the right thing is 4 pi a rho squared a, what we see right there. Now I called 1957 a golden year. Another of the really important papers, that's not a rigorous mathematical paper, but this was a paper of Lee-Huang-Yang, the C and Yang that I mentioned a moment ago. Lee, I think, is also still alive. They both got the Nobel Prize that year, not for this paper, because you usually don't get a Nobel Prize the year a paper is published. They got the thing for parity, the CPT, and the parity conservation. They were the youngest, some of the youngest ever to get the Nobel Prize. So I think Lee was the youngest American to get the Nobel Prize. He still is. He was like 26 at the time. And he's still alive. So they have been Nobel Prize winners for most of their life, Li and Yang. Huang was the younger person. He was a student of Yang, but he died. I mean, he died an old man. He was in his 80s. It's just that the other two keep on being alive. At least last time I checked, they were both alive. But they have an age where you should check every day. I mean, Yang is over 100. Last time I checked, he was alive, and he was over 100. But in 1957, they wrote a paper about Bose gases. And they were already convinced of the 4 pi rho squared A. So they went to the next term and predicted that the next term is a square root rho A cubed better. Recall that in the dilute limit, rho A to the dimension is small. So this rho A cubed is a small parameter. So this is a small correction to 1. And they have this beautiful constant, 128 over 15 square root of pi. Remember that number. I'll come back to it in a moment. So they claimed this formula. And this is what Dyson's paper came after. It's the same issue of Physical Review, but it's the next paper. Because Dyson said, oh, I should be able to prove this. So he was prompted by their work. And he was starting, of course, with the leading order and was able to get the upper bound. Let me point out that, so there are different length scales coming in here. So this comes from a length scale A, the scattering length. This comes from a different length scale that's called the healing length, which is 1 over the square root of rho A, depends on A. Now, it's difficult to have all these length scales in your head, but there are 3 important length scales for the dilute Bose gas. There's the scattering length. There's the interparticle distance, which is much longer because it's dilute. And then there's the healing length, which is again much longer than the interparticle distance. I'll get to the formula, because here are the rigorous results that we have for bosons. So 1, 2, and 3 dimensions, we have an expansion going beyond the leading term for bosons. So in 1 dimension, there's the result I mentioned, the pi squared over 3 rho cubed. 1 minus rho A to the minus 2. This term is what was correct to leading order for Lieb-Liniger. It was exactly correct for the hard sphere. And what we are claiming, and this is work with Agerskov and Reuvers, we're claiming that this is always the correct next to leading order. That's the little o of rho correction from there. In 2 dimensions, it's much more complicated. There was the rho squared, so there's a 4 pi rho squared. And then there's a correction that depends on the logarithm. There was this thing about the logarithm and the scattering length. So there's a log rho A squared to the minus 1. And then in 3 dimensions, there's the 4 pi rho squared A. I should emphasize that in 2 dimensions, this is not work that I was involved in. So this is Fournais, my former student, with his group. They were able to do the 2-dimensional case based on our work for the 3-dimensional case. Because what we proved in 2020 and 21 was indeed that the Lee-Huang-Yang correction is correct. So this was more than 60 years after Lee and Yang had written their paper. So the upper bound, so we can prove the lower bound. So we proved the lower bound. The upper bound had already been proved by Yao and Yin in 2009, and again by Bastisen and Chempo and Schlein in 21. But we cannot prove the upper bound for the hard sphere. We can prove the lower bound for the hard sphere gas. The upper bound is still unknown for the hard sphere gas. So there's still one case left to prove the Lee-Huang-Yang formula. One can only prove it for L3 potentials. So there's been a lot of work going into proving that formula. Now, what about fermions? What are the rigorous results for fermions? Well, in 3 dimensions, not that much is known. So there's a paper by myself and Lieb and Zeiringer, where we have sort of a spin 1/2, where we take the density spin up, density spin down. So it's like 2 free Fermi gases, one will spin up, one will spin down, and then there's an interaction between the two, the ups and the downs, as if they were the same, just giving the scattering length again, with the famous 8 pi A coming in. Now, we had a correction that was just very small compared to the leading term, and Giacomelli, she proved a better bound very recently. In one dimension, with Agerskov and Reuvers, we also studied what happened compared to the free Fermi gas. So the free Fermi gas was pi squared over 3 rho cubed. There is again an error that's of leading order in rho for small density. But the coefficient is interesting because the coefficient you get here, it depends. So when two fermions come close to each other, they may have the same spin or they may have opposite spin, if it's spin 1/2. But if they have the same spin, it's the type of scattering length you are studying is different, because if the particles have the same spin, their space wave function has to be antisymmetric. Whereas if they have opposite spin, the antisymmetry can be in the spin, and the scattering length they get when they get close to each other is closer to the bosonic scattering length. So that's why there are two scattering lengths coming in. The bosonic and what I call the fermionic scattering length, that's the one you get when you insist on antisymmetry in the two-particle scattering length calculation. But the interesting thing is that you get a coefficient that actually depends on the spin that you're getting. And the spin coefficient you get by solving a spin chain. So in the spin 1/2 case, it's actually the famous antiferromagnetic Heisenberg chain. In other spins, it's actually what's called the Lie-Sutherland model, which is a spin chain. It's not important what it is. It's kind of interesting that it's an exactly solvable model again, both for all spins, so in particular the spin 1/2 antiferromagnetic Heisenberg chain is exactly solvable. And I think this is probably the first time that you're getting the Heisenberg spin chain, the thing that tells you how, if you have spins sitting on different sides, how they interact in a specific SU2 invariant way, to get that very famous model coming out of a continuum model. So we start with a continuum model, and we're getting the antiferromagnetic Heisenberg chain as describing the coefficient in an expansion for the dilute gas. So I think this had not been done before. A few words about the experiments. So people studied this Lee-Huang-Yang correction. Whether you can actually see it, this was done in 2011 in the PhD thesis of Navon. He used lithium-7 atoms. Lithium-7 atoms, that's a boson. If you go to lithium-6, meaning you remove a neutron from the nucleus, that means you remove a fermion from the system, then you get a lithium-6 and you get a fermion. So lithium-6 is a fermion, so you can study fermion physics by looking at lithium-6. You can study Bose physics by looking at lithium-7. They confine it in a cylindrical trap, which is very long. It's 100 micron, but it's only 5 microns across. And they have a very dilute system, because rho a cubed, that's the diluteness parameter, is 10 to the minus 3. So on the scale of so you have to look at the scattering length. They look at 2 different scattering lengths. They can tune the scattering length by putting it in a magnetic field. It's a very clever experiment. So they can look at different values of the scattering length. But still more or less, rho a cubed is of order 1 over 1,000. So you have 1 in 1,000 particles seen on the scale of the scattering length. The healing length, which was the relevant thing for the Lee-Huang-Yang correction, is about 1 micron. And that's not very short compared to the 5 micron across. So this is maybe not really a thermodynamic system. I think the 100, that's fine. That's much longer than 1. But 5 is not much longer. So I'm questioning whether this is really a thermodynamic system. In any case, they calculate the Lee-Huang-Yang correction. So this curve here is the rho squared, and the green curve is what you get from the Lee-Huang-Yang. They calculate the pressure, and for the pressure, things are turned around, so you're subtracting by 128 over 50 square root of pi. In any case, they experimentally measure that number, and that number is 4.81. I mean, that's what you get if you plug it into your calculator. And if you do the experiment, they get that it's about 4.5. So it's pretty good for such an experiment verifying that quantity right there. Okay, let me give you an overview of how one gets to this Lee-Huang-Yang correction and what it has to do with superfluidity. Because what the gas does is that it does not go into a condensate. That would have way too high energy. It instead becomes superfluid. And Bogolyubov in 1947, another, this was not such a golden year because there was just Bogolyubov's paper, but there was a golden year 10 years later. So Bogolyubov studied superfluidity. So what did Bogolyubov say? He said, well, look at the particle number. Think of the projection onto constant functions, right? We want to look at the condensate. The condensate, these were constant functions. So in L2 of the box, let's think of the projection onto condensate and the orthogonal projection Q. Right? So the identity is P plus Q. So I can write 1 as P plus Q. Now, if I sum 1 over all the particles, I get the particle number, N. But then I can sum over the things in the condensate or things that are orthogonal to the condensate. And then I get 2 other numbers, or rather these are operators. I get an operator N0 and an operator N plus. N0 counts the particles in the condensate, and N plus counts what's not in the condensate. And then Bogolyubov says all the particles are essentially in the condensate. Well, that is Bose-Einstein condensation. We don't know how to prove this, but Bogolyubov didn't care in 1947. He said N0 is essentially N. That's the first step. And then he said, okay, take the potential, and really he did it in what's called second quantization, and I want to postpone this as long as I can. So I'm saying it in a slightly different way. The potential has a 2-particle interaction. So there's particle 1 and particle I and particle j. So I have an identity. I can put in a 1 and a 1 tensor 1 on one side and 1 tensor 1 on the other side. Because it's 2 particles, it acts on the space of 2 particles, and I can write it as P plus Q tensor P plus Q, V P plus Q tensor P plus Q. And then I can start expanding. Right? So there are 4 terms with P plus Q. When you lift these parentheses, you get 16 terms. There's a term which is P, P, V, P, P. That's the first one. And then the last one, Q, Q, V, Q, Q. And Bogolyubov said there are very few Q particles. So he says, ignore that term, that's small. And ignore the term with 3 Qs, that's also small. And actually, there are no terms with only 1 Q because of translation invariance, right? I mean, if you start with 2 particles that have no momentum, and then you cannot create a particle with no momentum and one with momentum, right? So there's a way to see that you cannot have only 1 Q. So if you ignore the 3 and 4 Qs, you have only no Qs or 2 Qs. So Bogolyubov said the 2 Qs I can solve. I can diagonalize that part of the Hamiltonian. So here's the idea of how to do this. So here is a term that has 2 Qs, Q, Q, V, P, P. Or you can have 1 Q on either side, P tensor Q, V, P tensor Q. Now I want to think of it in terms of what's called second quantization, creating particles out of the condensate. You should think of this as starting with 2 particles in the condensate and creating 2 outside. The potential throws out 2 particles from the condensate. And I write this as A star, A star. A, you should think of as an operator that pulls something out of Q into P, and A star takes you from P into Q. So this thing here is something that looks like A star, A star. And it has to be, it comes out with no momentum, so if it creates something with momentum minus P, it must give you also something with momentum P. In the same way, this thing has one that's not in the condensate and one that is and one that's not. The one that's not, you kill, and then you create one that's not. Right? So that's you just sort of leave one particle that's not in the condensate, and that, of course, is left with the same momentum. And then you can write the whole Hamiltonian in this sort of schematic form. It has terms that are A star, or terms that are A star A, or here A star, and AA. And I put plus and minus depending on what the potential is. And then you just complete the square. This is an identity. I complete the square. It's not complicated. The important part is you get a positive term and something which is, well, the commutator, which turns out to be almost 1. Meaning that what you have there is essentially the ground state energy. So that's what Bogolyubov did. He said, that's the ground state energy of my system. And indeed, if I look at that integral, plug in whatever I want, I get an integral which looks like q squared plus 1 from here, and then the square of that would be q to the 4 plus 2q squared. Then there's a 1 that's being squared, but that's subtracted by the b squared. So you get this integral from that formula. You integrate over all momenta. That integral is infinity. But there's a way to subtract something so that it's finite, normalize it, and out comes the 128 over 15 square root of pi. So one can do that calculation. It's not so complicated. Unfortunately, when you do the calculation, you do not get the scattering length. You get the 1 over 8 pi integral d, which is wrong. It would be infinity for the hard sphere. Bogolyubov knew that there was something wrong, and he has a very famous footnote in his paper that he asked Landau about it. He said, I'm getting 1 over 8 pi integral v, I think that's wrong. And Landau said, yeah, that's definitely wrong. It should be the scattering length. He had no idea why, but he thanks Landau for this important remark that this should probably be the scattering length. And it took us, well, from that time, over 70 years to really, no, I mean the Lieb and Ingwerson paper, so that is about 50 years from that time when they actually understood why the scattering length came in and not the 1 over 8 pi integral v. Now I'm essentially there. I just need to give you the proof. How do we do it rigorously? Well, I'm not going to tell you the proof, right? I'm going to do it very briefly. The problem with Bogolyubov was, let's go back, he ignored these q, q, v, q, q terms and the terms with 3 q's. Now, ignoring that term, you're throwing out the scattering length. It's a huge mistake. You should not do that. It's clear you do not want to throw. This term is not small. So with Fournais, we tried to find out what should we ignore. Is there something else we can ignore? And then we rewrote another, so V is positive, the interaction potential is positive. So we simply wrote a quadratic expression that includes the scattering, the omega, which was 1, u was 1 minus omega. We just said, this term here is also positive. So why don't we add and subtract this positive term? The positive part we ignore because it's for a lower bound, we ignore it. And the negative, when we're subtracting it, well, we'll remove the q, q, v, q, q, and it will renormalize all the other terms. So we managed to renormalize all other terms and essentially get the potential replaced by v. We still have the 3q terms, so we have to do sort of a Bogolyubov approximation, all this A dagger A business. We have to do it iteratively twice, so that's why the paper is 100 pages. But we finally managed to prove the LHY formula. But this is a very basic idea in our proof. So let me finish with some of the open problems. I mentioned already we do not have Bose-Einstein condensation. And then you may ask, well, how did you then do all this Bogolyubov thing? Well, it turns out that it's only the healing length that's relevant. And on the healing length scale, you can prove that there's Bose-Einstein condensation. I mean, imagine that you have this infinitely big system, but you look only on a box that's the size of the healing length. You put on glasses so that you can only see the healing length. Then it actually will look like there's a condensate. It's only on a very large box that we cannot see that all the particles are in the same state. In a small box, we can estimate it, they look like they're in the same state. And we can actually control it. But we would like to understand Bose-Einstein condensation in the thermodynamic limit. That's a holy grail. Higher order corrections for bosons would be interesting. There's a famous conjecture by Wu. I think maybe it's 1958 and 1957, but he did it. And it was very recently shown that in a confined system, if you confine to the healing length, don't go to the thermodynamic limit. Schlein and his group, actually, they were able to prove it as an upper bound. The Wu correction, the next correction after Lee-Huang-Yang. but we don't know it in the thermodynamic limit. As I mentioned, we don't have the upper bound for the hard sphere in 3 dimensions. Again, looks very, very difficult. And then we don't understand very well what's happening at in the high density limit. Well, to leading order, we have this. The 1/2 rho squared integral V that I mentioned to you is correct at high density. The correction to that is 1/2 rho V of 0. And notice you do not have universality. The first 2 terms depend on different parameters depending on V, whereas for scattering length, everything was depending only on A. But this was proved by Lee back in 1963. Lee, well, it's a little unclear whether it was actually rigorous at the time. He referred to some other paper, which may be not quite rigorous. You can prove this, again, by a Bogolyubov approximation, interestingly enough. So Bogolyubov is correct both at high and low density. And then positive temperature expansions. That's very difficult in the thermodynamic limit. It has again been studied a lot in a confined system. So thanks a lot for your attention.
So many thanks for this very nice talk. So do you have any question, remark, observation?
Sorry, there is one comment. There is actually one heuristic, non-rigorous argument for Lee-Huang-Yang is that you need it for the extended Gross-Pitayevsky to stabilize in some new cases, and that is experimentally validation, because the experiment by Navon is, it is finite dimension. Well, it is a direct proof of Lee-Huang-Yang. I don't know. I mean, I would like to comment on that. And the second question is, why you can always rephrase Bogolyubov as a variational, and then you can use the effective potential, what have you. In which sense is that, which is, as I would tell the story, why is it not rigorous enough? I mean, from theoretical physics, not from analytical physics.
Sure. No, of course, I'm not trying to anyway put down what's done in theoretical physics. I mean, the Lee-Huang-Yang paper is fantastic, that they no doubt about it. And so first to the Gross-Pitayevsky thing. So the Gross-Pitayevsky is in the confined case, and it's I don't know how much has been done in the confined case to next order beyond the leading the 4 pi rho squared A. I mean, usually Gross-Pitayevsky just does the rho squared correction in the usual Gross-Pitayevsky function. And the thing beyond that, I don't know how much it has been studied in the confined case. But so the thing I mentioned, the thing by Navon, which is actually the Christophe Salomon group in Paris. So as I said, it's questionable whether this is confined or not confined, right? Because it was 100 micron in one direction and 5 in the other. So whether you should use so the formula changes if it's confined, because you should use the confined scattering length. So I don't know much about what has actually been done experimentally in a confined situation. But you may say that the Navon, Salomon, Chevy thing was somewhat confined, but very long that I think you can apply the thermodynamic limit. I don't know anything else than that. The variational principle. So what is usually done, if you look at Huang's book, he actually studies the delta function potential. But there's a huge issue with the delta function potential from a mathematical point of view, that it's unstable. So it actually, we don't even, I mean, it basically doesn't exist. For bosons, the delta function potential, if you just in 3 dimensions write down the delta function potential, it's unstable from below. So you are not really studying the ground state, you're studying a metastable state. And as a mathematician, it's very difficult to even study metastable states. So I don't even know to rigorously validate what they did for the delta function. That it does give exactly the same formula is maybe not surprising, because you would think that a metastable state, if you waited for a long time, the state would eventually collapse. But of course, that's fairly long time, and at short time, since the thing is metastable, well, it's probably true that it's like a ground state of something that has the right scattering length. From a mathematical point of view, it's more interesting to the challenge is to study something which is stable and where you really know that you're studying the ground state. So that's the problem with this usual variational principle. So I also studied a variational principle for general potential with some of my students. If you take a potential V, not the delta function, but sort of a general potential, and in fact, if you do that for a general potential and you do a Bogoliubov variational calculation, you do not get the 4 pi rho squared A. You can get the integral V coming in. It's only in the limit as the potential nears a delta function that it converges to the 4 pi rho squared A. Unfortunately, that limit is not controllable in a rigorous way because it becomes unstable. The limiting point is unstable. So that's why we do not know how to study that mathematically. But it's a very nice calculation that you can do it for the delta function potential and you get the right answer. Mathematically, we don't know exactly what it is that we're calculating.
Okay, any other question? Mark? I have one question. Your potential is positive, no? Right?
Right.
What happens if I allow a little bit of negativity? I mean, of course, if it's too like a Lennard-Johnson with crystallization, but if you can you allow a little bit of negative part?
Okay, so you can allow a little bit of negative part. So in fact, I mentioned that the upper bound was proved by Yao and Yin for the Lee-Huang-Yang correction. So Yin actually studied the leading order term and corrections to that for potentials that are slightly negative. Mm-hmm. We believe that the theorem is true if you go to negative potentials under the following assumption, that you do not form molecules. Okay. Because if you form molecules, it should be the scattering length between the molecules that you should study. Mm-hmm. Now, this is a very difficult assumption because, well, okay, maybe you can form molecules of 2 particles, but you know sometimes you don't form it from 2, you form it from 3. So you would have to make a mathematical assumption that there are no molecules formed in any number of particles. And this is not a manageable assumption, right? I mean, I don't even know how to, I've actually been playing with it. I don't know how to write down a potential where I can prove it has a negative part and prove that it, for instance, has 2 body bound states, but no higher order bound states. Mm-hmm. If you could do that, then you could start studying the formation of molecules and the Lee-Huang-Yang gas of bosonic molecules interacting. But this is getting very, very difficult. So the assumption that Yin made was that it's very, very small, small enough that you can show from that there are no bound states in any particle set. Mm-hmm. But that's really the problem, the formation of molecules.
Okay.
But to that point, I really don't know. I have no idea. What's the status of the characterization of potentials for which Efimovs can appear and cannot appear? So I really don't know what the status is.
I mean, this is a huge this is a huge subject, and there are pretty good characterizations. So the Efimov is when you can have 3 body but no 2 body bound states. But of course, that's not enough. We also have to say that there are no 5 body bound states. So even if you have no 2 and no 3, you don't have any 5 body bound states. But of course, one thing you might study is what is sometimes studied for the Efimov effect, not potential, but rank 1 perturbations, right? So that you put in a projections instead and then do a limit. So that problem has not been studied. The only problem we've studied is the potential problem, where particles interact by an energy depending on the distance. But you could study the thing where you have that when 2 particles get close, it's an operator, it's a projection, it's a rank 1 projection in the 2 particle sector instead. That is probably a way of doing the delta function more rigorously in a limit, but that has not been studied.
Any other question? Maybe a last one. You say that with Bose-Einstein condensation you are not able to do it because of you just look on the size of the healing lengths.
No, and I'm saying on that scale you can do it. I mean you can
do it.
Yeah, you can. I mean you can ask. You can take a box, put in bosons that interact, and ask if most particles are in the condensate or not. If you take a box in the for very dilute systems, you can take a box of the size of the healing length, which is you have many particles in there. This is a length scale much larger than the interparticle distance. On that length scale, and we do it in this paper, and Fournais wrote a separate paper where he did it explicitly, pushed it as far as he could. You can prove that if you confine your system to such a box of the slightly longer than the healing length, then most particles are in the condensate. Now, what happens if you go to a larger box? Well, so on this scale, you see everybody being in a constant function, right? So but then as you start doing a larger box, maybe they are constant here, but maybe it just means that the momentum is very small. So they vary on a scale that's very, very long compared to that scale. And that means that you basically, what you're proving is that you're spreading out the particles in momenta that are 1 over the healing length. And that's all you can prove. What you want to prove when you prove condensation is that all particles, not all, but most particles, a finite proportion of the particles are in momentum 0. But this we cannot prove because they may vary very slowly. You cannot prove it by energy estimates because you cannot control, you would need to control the energy to an order that gets smaller and smaller as the box gets larger and larger. At least that would be one approach to try to do it in that way, but nobody has succeeded. There are people trying to do it probabilistically, writing it maybe as a Feynman-Katz formula, thinking of path and long path. And there are people that have tried to do it by using constructive field theory, so rewriting the whole system as constructing a quantum field theory that describes it. This is the group in Zurich that has been trying this, and they've had some progress, but it's still not, they've not been able to prove condensation. No, all the different groups, all the different attempts have not been able to prove condensation beyond boxes that are slightly bigger than the healing length.
Okay, so if there is no other question, many thanks again to